This video introduces reinforcement learning. We want to make a sequence of decisions to reach a desired goal. Take for instance an exam situation. Some days before the exam, you need to decide whether you want to work and study for the exam, or whether you want to enjoy life and go to a party. Passing the exam will give you a reward of +10, while failing the exam costs -10. You start in state U0, several days before the exam. Each day you can choose to study, to follow a green arrow, or to party, to follow a red arrow. Since partying is more fun, you get an instant reward of +1. Studying on the other hand always costs -1. Depending what action you choose, you get to a new state, either a bit closer to passing the exam or a bit closer to failing the exam. But there are more choices for actions, and maybe you can afford to go to some parties. If the decision process is like this, what actions would you choose to maximize your total reward? Please pause the video and think about this for a minute. Clearly you want to pass the exam, since passing the exam gives you a juicy reward of +10 points. But there are several ways to get to the passing state. The one shown here with the wiggly arrows gives the highest rewards. You first party for +1, then you study twice for -2, and finally you pass, with +10. So in total your reward is +9. Well done, you achieved the maximum possible reward. However, reality is often not deterministic, and some of your actions might have probabilistic consequences. Indeed, studying may only help with some probability, and partying might even be helpful in some cases. Assume that all the thick arrows have a probability of 70%, while all the thin arrows have a probability of just 30%. What's the best expected total reward you can get now? And what are the actions that you should take in each of the 4 states? This is a good example of a so-called Markov decision process, or MDP for short. Generally, an MDP consists of 5 parts. First we need the states, as shown with the circles and boxes. The circles are intermediate states where further actions can be taken, whereas the boxes show final states. Next, we need actions. In our example there are just 2 possible actions, study or party. Then, we have a transition function. In each state we can take one of the possible actions. Each state action pair gives us a probability for a possible next state. Here we show these transitions with arrows in a graph, but transitions can also be specified as a table. An MDP also needs a reward function. Rewards can be positive or negative. One can get a reward by either visiting a certain reward state, or by taking an action in a state. In our example we have both. Finally, one of the states is the starting state. In our case we start at state U0. It's also possible that we have several starting states and a probability distribution, which then tells us where to start. In reinforcement learning, we want to compute the best actions, which maximize the total reward. Let's start our understanding at state U3. In U3, we can either study or party. If we study, with 70% probability we pass the exam, and with 30% we fail. So if we study, our reward is -1, that's the penalty for studying, and then 70% times +10, and 30% times -10. Altogether, the expected reward sums up to -1 + 7 - 3, which is +3. On the other hand, if we party in U3, then we can get an instant gratification for partying of +1. But then with 70% probability we fail the exam for -10, and only with 30% probability we pass the exam for +10. If we sum this up, we can have a total expected reward of +1 - 7 + 3, which is -3. So if you are in state U3, in expectation, partying gives you -3, while studying gives you +3. So, without doubt, it's better to study, for an expected reward of +3. Now we can focus our attention on state U2. The 2 possible follow-up states are either failing the exam for -10 reward, or state U3, with an expected reward of +3, as we have just computed. We can do the same math as for state U3, and conclude that also in state U2, studying is better. The reward for studying in U2 is -1, this is again the instant negative reward for studying, plus 70% times 3, minus 30% times 10. All in all this is -1.9. This is not great, but still better than partying, which gives an expected reward of -5.1. So the expected reward with the best possible action in state U2 is -1.9. With this we can go to state U1. If we do the same math again, we see that this time both actions are really close, but indeed partying beats studying in U1. And so we go to the starting state U0. When doing the math we conclude that again partying in U0 is better, for a total expected reward of roughly -0.16. This is exactly how one classic flavor of reinforcement learning works. We build a matrix, known as the Q matrix. The rows of the Q matrix are all the states, and the columns are all the actions. For each state-action pair we then compute the expected reward. If the MDP is a directed acyclic graph, we can simply directly compute all values, starting at the states closest to the terminal states of the MDP, and then moving towards the starting state, as we have done in our example. If the MDP has a cycle, this is more difficult, since the value of a cell in the matrix may now depend on itself. In this case we update all values in all the cells repeatedly. If we update a cell's value, this might affect the values of some other cells again. We repeat this update procedure until the values barely change anymore. Note that it is generally not guaranteed that we find a solution this way. When computing a value of a cell in the matrix, we directly include any immediate reward that we are getting in that cell. And then we add the expected rewards of the directly following states, the same way we have done it in our study party example. However, those next cell rewards we multiply with a factor gamma, which is a hyperparameter between 0 and 1. The idea of gamma is that we cannot be 100% sure about the future. When taking future rewards into account, a gamma less than 1 will help us to not be overly optimistic about those future rewards. The hyperparameter gamma is often known as the discount factor, so the next reward is discounted by gamma, and the next reward by gamma squared, and so on. Finally, the so-called policy describes which actions we take in which states. This policy may also be probabilistic, that is, in some states we might choose actions with certain probabilities. A policy is optimal if it maximizes the total expected reward. In summary, in this video we introduced reinforcement learning. We showed how to compute the optimal policy if the Markov decision process is a directed acyclic graph. And we discussed how to update the Q matrix using the gamma discount factor if the Markov decision process is cyclic. Thanks for watching this video.